Alright, hello, welcome to today's mathematics class, stochastics processes. So today we'll be talking on Markov chains, and then Andreyevich Markov is a Russian mathematician whose contributions actually impact stochastics process. And the summary of Markov chain is this particular quote. See, it only matters where you are, not where you have been. So this quote captures the work of Markov in the stochastics process. So before we define Markov chains, let's define some terminologies that we'll be using in Markov chain. Okay, so first let's define the state. First definition is the state of a Markov chain. State of a Markov chain at time t is the value of x index t. So when we talk about the state of a Markov chain, we actually need the value of your random variable at time t. For example, if x index t is equals to 6, so we say the process is in the state 6 at time t. So take note of that. So if s index t equals to 6, then we say that the process is in the state 6 at time t. So let me make another example for better understanding. So if you have x in the 2 equals to, maybe we are dealing with weather forecasting, equals to raining. So we say at time t, at time t equals to 2, the process or the system or the weather condition is raining. Okay, so let's check another term. Definition 2. Let's talk about the state space now. The state space of the Markov chain so represent as x is the set of values that each s subscript t your process can take. For example, now if your process or your system is a fair-sided dart. A fair h6. And for example, we have a 6-sided die. So you should know that your state will be 1, 2, 3, 4, 5, 6. So we have discussed this in our previous class, but we actually need it if we are doing weather forecasting. Or if you are dealing with a coin, use a coin, your state space will be head, tail. So that is the configuration of a coin, and that means state space. State space also means the collections of all your states. The collection of all your states of a particular system. So take note of that. So definition 3. A trajectory of the Markov chains is a particular set of values for x0, x1, x2, right. So let's take some example and let's understand this definition properly. For example, if we refer our for example, if x0 is equals to 1, that is the process at time t equals to 0 is 1, the process at time t equals to 1 equals to 5, and the process at time t equals to 2 equals to 6. Then the trajectory up to time t equals to 2, that will be, and that is at s subscript 2, that will give us, that is 1, 5, 6, 1, 5, 6, because this at time t equals to 0, t equals to 1, and t equals to 2. So the path, in other words, that's another word for trajectory, we also call it path. So that is the path of the process up to time 2 is 1, 5, 6. So more generally, if x0, x1, x2, x3 denotes the trajectory then we can have our x0 to be x0, x1 to be s1, x2 to be x2, x3 to be equals to x3 ... Okay, so trajectory also means path, so take note of that. So definition 4. So we can now discuss Markov property. Markov property. Okay, we said in Markov property we have the probability distribution of our next or our future state, given that the probability of our current state is common t and our previous state is t comma minus 1 dot x naught equals to s naught is equals to probability distribution of our future state is only depending on the probability of our current state. Alright, for all t equals to 1, 2, 3 dot and for all states x state x naught, x1, x2 dot. So this Markov property, and the literal meaning of this is that property is that it means that xt plus 1, that is our future state, only depends upon our current state, but does not depend upon our previous state. And depend upon our previous state. So let me give a simple definitions for this, or a simple example for this, so that I can just move on. For example, let me do weather forecasting now. So the Markov property, we have probability distribution of the weather condition tomorrow. This connects tomorrow's weather, where this s subscript t subscript t equals to s subscript t. This connotes today's weather, dot st minus 1. This connotes yesterday weather, dot the day before yesterday, and etc. So Markov property says that for us to predict tomorrow's weather, which is s subscript t plus 1, we only need to consider today's weather. Hope you can get that. So this connotes this distribution of st squared, is also called of your future, the future state. This depends on t. This is your current state, and these are your previous states. So Markov property says that actually the weather condition tomorrow is your future state, only depend on your current state. That's Markov property. So let me change my pen for better understanding. So this is tomorrow's weather. Sorry. The future weather, while this the current weather. Why this could not yesterday weather, the day before yesterday weather, etc. So the Markov property is that it wants to predict tomorrow's weather, which is future weather. Just consider today's weather, current weather. So I believe with that example, I'm able to grab what the Markov properties is all about. So lastly, let us now define Markov chain. Markov chain. Okay, so let's set up our random variable x0, x1, x2, dot be a sequence of discrete random variables. And so then x0, x1, x2 dot is a Markov chain if it satisfies the Markov property. We satisfy the Markov property, which is the probability distribution of your future state given that your current state is xt, dot your previous state is equals to your future state, the future state depending only on your current state. Okay, I believe that is clear enough for you to understand. So for all t equals to 1, 2, 3, and for all states x0, x1, dot x script 3 x. So you can see that Markov chain, we are for us to predict the future state, we just have to depend on the current state. So that is why these codes capture everything about Markov chain, that it only matters where you are, not where you have been. Alright, so we stop here for today. Thank you for watching. See you in the next class.